Hello everyone, welcome to lecture number 2 of third week. In the lecture number 1, we have seen that the basic definition of subsequences and an important theorem about subsequences that if a sequence converges to a limit point L, then every subsequence of that sequence converges to the same limit point L, right? So now we will, in this lectures, we will explore much more theorems based on the subsequences and how these theorems help to understand convergence, to check or investigate convergence of a given sequence. So the theorem consists of monotonic increasing and monotonic decreasing, and based on these monotonicity of a sequence, we will assure that what will be the qualitative behavior of the subsequences. So let's say every subsequence of a monotonic increasing sequence of real number is monotonically increasing, right? So we will prove that one mathematically, and we will see the examples related to this theorem. So property of a monotonic subsequences, theorem states that xn be a monotonic increasing, let's say monotonic decreasing, whatever sequences of real numbers, then every subsequences of that sequence xn is also respectively monotonic increasing or decreasing. That will be our both theorems in one statement. For time being, let's suppose that monotonic increasing sequence is given. So xn is a monotonic increasing sequence. So what will be the meaning of that monotonic increasing sequence? That means each term of that sequence is greater than the preceding term. So that means we have 1, 2, 3, 4, 5, 6, 7. So n is the sequence. Then look at any term. So look at 4. 4 must be greater than 3. Look at 7. 7 is greater than every preceding terms here, 6 and so on, 1, 2, 3. So xn is less than or equal to xn plus 1 for every natural number n. Every natural number n, right? That is our definition. Now consider any subsequence xnk whose indices are nk. Indices are nk, and nk we have already know that if it is a subsequence, then nk must be monotony increasing itself. So since subsequences retain the original order of indices, while skipping some elements, we still have n1, n2, n3 and so on. The same order as we have. So that's why xn is a monotonic increasing. We get xn1, xn2, xn3 in order, and that means the subsequence must be monotonically increasing subsequence. Similarly, consider monotonic decreasing sequence. That means every term is less than the preceding terms. So we have something like 1 by n, and as you can see here 1, 1 by 2, 1 by 3, 1 by 4 and so on. Then look at the any fixed terms 1 by 4 or so on. It is less than 1 by 3. Such a sequence is called monotonic decreasing sequence, right? And look at considering by nk as a indices, and since nk retain their order, therefore xn1, xn2 and xn3 and so on also retaining their orders, retaining their orders. And that means what? That means xn must be greater than and equal to xn plus 1. That means it is a monotonically decreasing subsequence. So these are the proofs by using their orders and by looking at the monotonic increasing and monotonic decreasing conditions, we can prove that if a sequence is monotonically increasing, then every subsequence of that is monotonically increasing. If a sequence is monotonically decreasing, then every subsequence, if it is monotonically decreasing, then it is also monotonically decreasing. Similarly, look at some examples for that. So first example is taken by natural numbers 1, 2, 3, 4, 5 and so on, right? And look at even index, so 2, 4, 6, so on. So this is also making a subsequence. Now what will be the qualitative behavior of this subsequence? So check for this. So xn plus 1, I am checking this one, xn plus 1. So let us say 8, it is greater than or equal to xn each time. So this is a monotonic increasing sequence. Similarly, look for odd index. So 3n actually. So 3, 6, 9, 12 and so on, and in which we have also seen that xn plus 1 is greater than xn, and so it is a monotonic increasing sequence. So all are monotonically increasing sequence. Similarly, consider a sequence 1 by n. This is a sequence, and as in the previous slides you can see here, this is a monotonic decreasing sequence, Consider x2n and x3n. x2n, what will be the value? 1 by 2, 1 by 4, 1 by 6 and so on. This is also a monotonic decreasing sequence. Similarly, x3n, 1 by 3, 1 by 6, 1 by 9, 1 by 12. This is also a monotonic decreasing. So all these subsequences are monotonic decreasing sequence. Similarly, the third problem consists of one example, that is 2p power n. So all the sequences, the terms consist of 2p power n. So the first term is 2, the second term is 4, 8, 16 and so on, right? And as you can look at this here, xn plus 1 is greater than, strictly greater than xn, and henceforth it is a monotonic increasing sequence. So look at another subsequence or another sequence which consists of x to n. So their terms are 4, 16, 64, and in which we have also seen that xn to n, the preceding terms for xn to n, the xn plus 1 is always greater than this term, is always greater than these preceding terms. So it becomes a monotonic increasing sequence, right? Now if you remember the in example of a Fibonacci sequence, where we have defined a Fibonacci sequences in a sequence wise, fn minus 1 plus fn will give you the fn plus 2 terms, right? Where f of 0, f of 1 is given 1, f of 0 is given 1, right? So 1, 1, 3, 5, 8 and so on, right? So that was the Fibonacci sequences. So here for this sequence itself, if you look at the indices as a Fibonacci, 1, 1 and so on. So what will be the terms? The terms will become 2, 4, 8 and 32, and all these terms are increasing. So this is the monotony increasing subsequences. Consider a subsequence again 100 minus n, 100 minus n. So that means n equal to 1 will give you 99, 98, 97, 96 and so on, right? And how many terms? It will consist of not only the positive 99 to 0, but it also going to be 0 to minus infinity. So huge, this is a sequence of infinite terms. Now consider x to n, so even index terms. So what will be the first term? N equal to 1, this will give you 100 minus of 2, right? So this is a 2, so this will be a 98. Similarly the next one is 96, similarly the next one is 94, 92, 90, 88 and so on. Now look at the terms. This is a decreasing sequence, so this is monotonically decreasing sequences. Similarly, look at x3n. What will be the terms it held? 99, 96, 93, 90 and so on. So these are also the terms, and this is also monotonic decreasing. So that means the theorem is valid, and it will help us to recognize a qualitative behavior of a given subsequences very easily. Now based on the monotonicity of a subsequences and boundedness, we can have the convergence of that monotonic sequences, right? I believe that you remember the monotone convergence theorem, where we have understand that if a monotonic increasing sequence there is and it is bounded above, then it must converges where? It must converges to least upper bound, right? And similarly, a sequence which is monotonic decreasing sequence and it is bounded below, then it must converges to greatest lower bound, that is infimum of that sequence. That was the theorem previously, which is also called monotone convergence theorem. Here we use that one and we connect that relationship with the sequence to subsequences and given monotonicity, right? So in the framework of monotonicity, we are going to relate each other sequences to subsequences. So what the statements? I am going to read it. A monotone sequence xn of real numbers, if it has a convergence subsequences with limit L, then the entire sequence xn is convergent and has the same limit L. So now look at monotonic, the frame is given, this is the monotone. So that means the sequence is either monotonic increasing or monotonic decreasing. And if that sequence has the converging sequence, subsequence, that means converges to some limit point L, then the sequence itself converges to the same limit L. Can you imagine that if a subsequence is converges to some point limit L, then is it necessary to a whole sequence converges to the same limit point? No, you cannot have. Why? Because if you remove the monotonicity, it is only valid when it is a monotonicity framework are there. If you remove that monotonicity, it cannot be. So one simple example is, take a constant sequence, subsequences 1 1 1 and minus 1 minus 1 minus 1. These are the two subsequences of a given given sequence, minus 1 per power n divided minus 1 per power n, right? Which is not a converging. Subsequences are converges to 1 and minus 1. So, but the sequence is not converging, it is oscillatory. So, it's not a, it's a non-convergent sequence. So, that's why monotonicity for subsequences converges leads to a sequence converging is important. And now I will prove that. So consider for simplicity that xn is a monotonic increasing sequence, right? Then since it is given that if the sequence has a convergent subsequence, so let's say xnk be a subsequence and it converges to a limit point L. So for every epsilon is greater than 0, there exists a natural number k0, right? We have already done this, right? This is a k0 is a natural number depending on epsilon itself, such that xnk minus L is less than epsilon for all k is greater than equal to k0 as some natural number at k0. So thus for every n which is greater than nk0, now indices, and k0 is a fixed point here, fixed number. So nk0 is a fixed indices, right? So for all n greater than nk0, we have xn which is less than xnk, because you have monotonic increasing sequence. So that means nk0 and nk and so on, all these are what? All these are valid because the indices are monotonic increasing sequences of nk. So xn is less than xnk and xn is given, xnk is less than L plus epsilon, because you have to explore this one. This is nothing but L minus epsilon is less than xnk is less than L plus epsilon. So we are going to use the right hand side of this. So this is the, so we now we have here as xn is less than L plus epsilon. That's for sure. Since the sequence is increasing, that's we have used this. So now since the sequence increasing and xnk less than xnk tends to L, it follows that xn must be greater than x1, and henceforth we have all those terms of the sequence are bounded above by L plus epsilon and it is bounded below by it's the first term x1. It means all terms of the sequence xn after a certain point, some of the point m is given here, stay between x1 and L plus epsilon. That means xn must be bounded ever by this capital L, and by monotonic convergence theorem we knew that every monotonic increasing sequence bounded ever must converge, and it converges to its supremum. So what will be the supremum? Least upper bound, least upper bounds, right, LUB. So it converges to L as n tends to infinity. That will be the theorem for case 1. Similarly, we are now going to explore for monotonically decreasing sequences. So suppose xn is a monotonic decreasing sequence and a subsequence xnk is given which converges to the point real number L. So by the definition of convergence, for every epsilon greater than 0 there exists k0 is a natural number such that xn k minus L is less than epsilon for every k is greater than equal to k0. And but here for all n is greater than nk0 we have xn is xn now is not this one, but xn now is greater than xnk, right, all the indices, because it's a monotone decreasing, and each xnk, look at this one, xnk is less than L plus epsilon, use this one. So each xnk is greater than L minus epsilon, right. That means xn is bounded by with lower bonds, and what will be the greatest lower bond? The greatest lower bond is L. So this is the bounded below, xn is a bounded below. This is wrong. The right one is here. What will be the written one? Xn is greater than or equal to xnk is greater than L minus epsilon. That will be the right equations. And xn is greater than and equal to L minus epsilon for every k is, and so on. Every n is greater than k0 and nk0. So that means it is a bounded below, and by monotonic convergence theorem, every monotonically decreasing every sequences having the lower bond converges to their greatest lower bond, that is infimum. Now we will going to explore some examples. So taking 1 beta n and subsequence x2n. So we knew that it's going to be converging to be 0, but so entire sequence xn here is going to also converging to 0, and how we can prove this one that it is true. So let's explore this. So firstly we have to find out that sequence must be monotone. That means either it is monotonically increasing or either it is monotonically decreasing. So 1 by n is monotonically decreasing sequence. That's all, the first one. So this is the first criteria for the theorem. Now look at the subsequences. 1 by 2n, this is converges to 0. So the capital L is here 0 and it is a converging subsequence. So this is the second point of the theorem. Now if it happens, then the sequence, not the subsequence, but the sequence converges to the same limit point as it has the subsequence. So where subsequences converges, it is converges to 0. So the 1 by n, the sequence also converges to 0. That is by the theorem itself. Similarly, look at another sequence n divided by n plus 1. Now it is also a decreasing sequence, isn't it? So this is some of the terms are 1 by 2, 2 by 3, 3 by 4 and so on. This is a monotonically decreasing sequence, right? And consider a subsequence 2n by 2n plus 1. Now look at 2n divided by 2n plus 1, and here is the limit n tends to infinity. It will gives you 2 divided by 2 plus of 1 by n, limit of n tends to infinity. So this will give you 2 by 2 is cancel out is 1, right? So this subsequence is a converging subsequence and converges to a point capital L which is equal to 1, right. So that means since sequence is monotonic decreasing, so a monotone framework, we see that this subsequence, if it is a converging, then the sequence must converges. So where it converges to 1. Where it converges to the 1 without any mathematical calculations, right. Similarly, look at the sequence 100 minus 1 by n, 100 minus of 1 by n. Can you tell me what will be the qualitative behavior of that sequence? Is this a monotone sequence? Yes, it is a monotone sequence. Is it a monotone increasing or decreasing sequence? Yes, it is a monotonically decreasing sequence. The first term is 100 minus of 1 is equal to 99. Second term is 100 minus of half is equal to 99.5. Third is 100 minus of 3 is equal to something 99.7699 and so on, 7 something, right. So that means it is a monotonically increasing sequence. It increases, right. Why? Because 1 beta n is monotonically decreasing and minus is written here. So whole this sequence now become a monotonically increasing sequence. Now look at the subsequences 100 minus 1 by 2, and this is a subsequence. And now we will explore that is this a converging subsequence. So firstly check whether it is a converging subsequence. So limit n tends to infinity, 100 minus of 1 by 2n. So 100 limit of n tends to infinity, 100 minus of limit of n tends to infinity 1 by 2n. This will become 0. So this will become limit of n tends to into infinity 100. So the answer is 100. So it is a converging subsequences and having the converging limit point as 100, limit as 100. Now without any calculations we can say that this monotonic increasing sequence xn equal to 100 minus 1 by n also converging and converges to the same limit point 100. That's all. So now consider another one, 1 by n square. This is a sequence. What will be its qualitative behavior? So this is 1, 1 by 4, 1 by 9, 1 by 16, 1 by 25 and so on. So this is a monotonically decreasing sequence. It decreases, right? And this is a monotonically decreasing sequence. So we have a monotone framework and monotonicity as a framework, and the subsequence is given 1 by 2n square. So firstly we will check that it is a converging subsequence or not. So n tends to infinity 1 by 2n ka whole square, right. So it will going to be 0. So it is a converging subsequences converges to 0, right. So L is equal to 0 here. So the without any check we can say that this sequence is converging and converges to the point 0. Now some of these theorems are quite useful for you, and it must be remembered the results are applicable everywhere, and the results are very much applicable to investigate the convergence of the given subsequences or sequences. A necessary and sufficient condition for the convergence of a monotonic sequence is that it is bounded. So what is the necessary and sufficient condition for the convergence of a monotonic sequence? It is a bounded, and we had already proved that, right. So what will be the corollary? A monotonic increases bounded above sequence converges to its least upper bound, that means its supremum, and monotonic decreasing bounded below, where it converges to its greatest lower bound, that means where its infimum. Corollary 2, every monotonically increasing sequence which is not bounded above diverges to plus infinity. Similarly, every monotonically decreasing sequence which is not bounded below diverges to minus infinity. Based on these theorem and the corollary of this theorem, we will investigate the convergence of sequences qualitatively and use this theorem as a necessary condition and sufficient conditions. So, as with this the subsequences can have the similar property, and in the next lectures we will go through that monotonicity and subsequences and how it helps to get or investigate the convergence of a given sequence or subsequences. So, now this is the end of this lecture. So, thank you so much.